Okay, hello and welcome to lecture 2 of the week. We were working on vectors when we were interrupted by the end of class last time. And we're still in vectors in 1 dimension, have a little bit more to do with that, and then we can get into 2 dimensions. We will start with the example that I was just about to do at the end of class. It's a little, it was too long to fit into the couple of minutes we had at the end of class when we met in person. So here it is now. If you remember last time, we had just finished going over some of the basic rules for adding and subtracting vectors. And as long as vectors are in the same direction or the opposite direction. In other words, as long as the vectors are parallel to each other or anti-parallel to each other, then adding and subtracting them is very simple. You just basically add or subtract their magnitudes. Things get a little more complicated when they're in 2 dimensions because they don't necessarily have to be going in the same direction or not. But basically, if you're dealing with 1 dimension, then you're dealing with a line, and everything pretty much has to be in either the same or opposite directions in 1 dimension. So this example is, say, if you're traveling from Buffalo to Rochester, and Buffalo is point A and Rochester is point B, as we did with the examples in class. And say you get to a point that's 3/4 of the way between Buffalo and Rochester. We'll call that C. And you drive 12 miles back towards Buffalo. And we'll call that point D. So you're driving from Buffalo to Rochester, you get maybe 3/4 of the way to Rochester and discover that you forgot your teddy bear. So you have to turn around and go back and get your teddy bear. But when you've driven 12 miles back towards Buffalo, you remember you threw the teddy bear in the trunk. So you have it after all, everything's fine. And now you can turn around and go back to Rochester. But we're going to cut things off at that point and see how it stands. So you got point A, which is Buffalo, and point B, which is Rochester. And what we've done here is we started at point A and went to point C, which is about 3/4 of the way to Rochester. And then we drove from point C back to point D, about 12 miles. And I think that these, the ways I'm drawing these vectors is fairly proportional. And so the question is, what is your displacement at point D? Or in other words, what is the vector say it would be DAD. What we have here on this plot so far is we have the magnitude of the vector from A to B, that is Buffalo to Rochester, is 60 miles. The magnitude of the vector from A to C would be 3/4 times 60, or 45 miles. The magnitude of the vector from A to D should be basically 45 minus 12. You had a magnitude of the displacement when you went from A to C was 45 miles. Then you went back 12 miles. So that's 33 miles. Okay. At that point, if you were then to turn around and go to Rochester as your original destination, then, whoops, let's extend this down here. The magnitude of the vector from D to B, how far you would have to travel from point D to get to Rochester, that would be basically 60 minus 33. We found out that this distance here from A to D is 33. The distance all the way from Buffalo to Rochester is 60. But if you're starting from a point that's already 33 miles into the journey, then your distance will be 60 minus 33, or 27 miles. So things are pretty easy when they're in one dimension. For the vectors, the vector from A to C would be 3/4 or 0.75 times the vector from A to B, which is 45 miles. And remember, for a vector, you have to specify the direction. So that's 45 miles east. And that is your displacement at point C. Okay. The vector from, C to D is anti-parallel to the vector for A to B. Okay, so the magnitude of that vector is, the magnitude of the vector. In other words, it's the absolute value of the vector. Because this is where you're going from C to D, that is 12 miles back towards Buffalo. And another way of putting that is 0.2 times the vector from A to B. And we get this 0.2 is basically 12 divided by 60. The vector from A to B would be 60 miles. 12 miles is a proportion of that, is 12 over 60, or 0.2. So if you want to put this magnitude in of CD from point C back to point D, if you want to put that in terms of the overall distance from Buffalo to Rochester, then that would be 0.2 times the total distance. And so the vector CD is negative 0.2, or 0.20 if you prefer, times the vector from A to B. Negative because you're heading backwards. The direction is negative. The total displacement from Buffalo would just be the vector sum of the displacement vectors. Buffalo is point A, so I'm just going to abbreviate it as A. And that would be vector DAC plus vector DCD. And that would be the vector from A to D. Okay, so the resultant, in other words, would be DAC plus DCD, and that would be equal to 0.75, the vector AB, minus 0.2 times the vector AB. So we've got it in terms of the total trip. And you can bring together the scalars and multiply them collectively by the overall vector. And that is 0.55 times the distance, or the vector for AB. Let's see, the magnitude of the vector, if you want that. Working it out this way, we worked it out as sort of just like a basic number line problem up here. Working it out through vectors, the magnitude of the vector from A to D would be 0.55 of the magnitude of the vector from A to B, and that's 0.55 times 60 miles. And 0.55 times 60 miles is 33 miles, which is exactly what we found up here, just doing it as a number line problem. And yes, it was simpler to do it this way as a number line problem up here, but this is a very simple problem. There will be ones in the future that are much more complicated than this. And so we were doing this as sort of a way of checking ourselves. Doing it this way using the vectors will be a lot better for the more complicated problems. Okay, the total displacement once Rochester is reached that's assuming that once you get to point D, you remember you have your teddy bear in the trunk after all, and you can turn around and go back to Rochester. So your total displacement once Rochester is reached is, of course, 60 miles east. But we knew that to begin with. But we can also find that the vector from A to B is the vector sum of all of the segments of the journey. So looking at the segments, the vector from A to B should be equal to the vector from A to D plus the vector from D to C plus the vector from C to B. And the problem is the vector from C to B was never actually measured. I mean, you can work that out as kind of a number line problem, but it was never worked out through vectors. But if you look at this total here, DC plus CB, that is equivalent to the vector DB. And so you can substitute that in for both of these terms, and we end up with the vector from A to B being equal to the sum of the vector from A to D plus the sum of the vector from D to B. Okay. And the vector from D to B is equal to the vector from A to B minus the vector from A to D. And that is equal to the vector from A to B plus the negative of the vector from A to D, because you're going back there. Now, we finally got it in terms of things that we've actually measured. Okay, so the vector from D to B is going to be equal to the vector from A to B minus the vector, because plus a negative is the same as saying minus, from A to D, and that is going to be vector from A to B minus 0.55, the vector from A to B. Another way of saying that is the vector from A to B is equal to 1 times the vector from A to B, obviously. Anything is equal to 1 times itself. And you're subtracting 0.55 of that. So you can condense the scalars again, with 1 being understood as the scalar that this is being multiplied by, and 0.55 being the other one. 1 minus 0.55, oops, 1 minus 0.55 times the vector A to B. 1 minus 0.55 is 0.45. And so 0.45, your vector from A to B, is the vector from D to B. So it was a bit of a long process, but we do get there. And I'm going to squeeze this in down at the bottom because it's relevant. The distance would be from those 2 points. Oops, distance is 0.45 times 60 miles. And 0.45 times 60 just happens to be 27 miles, which we found up here already, just treating it as a number line kind of problem. So that's kind of an overview of how to do something like this using vectors that have actually been measured. As I said, there will be more complicated problems we get to in the future where doing it by vectors will actually be easier than trying to do it this way, particularly when we get the things in 2 to 3 dimensions. Like I said, things are really easy and straightforward when you're in 1 dimension. That's why we do that first. And then we expand to 2 and 3 dimensions so that we can learn to sort of expand the same techniques. Okay, so if the vectors lie along the same line, in other words, they're parallel, then the resultant is just A plus B, vector A plus vector B. That's a bit of a review from what we've seen. The difference of the vectors would be vector A minus vector B. If you're adding vectors, remember, just like numbers, it doesn't matter what order you add them in. But if you're subtracting, it does matter what order you subtract them in, because this is equivalent to vector A plus negative vector B. Okay. For the magnitudes, the resultant would just be the magnitude of A plus the magnitude of B. For the difference, the magnitude, since the magnitude always has to be positive, remember, in vectors, negative denotes direction. Magnitude is always positive. You would take the absolute value of the difference. And for addition, of parallel vectors, they can basically you draw them head to tail. And you can do it in any order. So the resultant for the vectors, for vector A plus vector B, you could just draw vector A and vector B head to tail like that. You could also draw them like this. And that would come out to the same thing, assuming that I had actually drawn vector B to the actual same length that I drew it before. But yeah, I mean, if you're drawing them carefully, that would be the same thing either way. And for subtraction of parallel vectors, which remember is that essentially the same thing as addition of anti-parallel vectors. You can draw them either head to head or tail to tail. So you could draw them like this. Actually, I wanted them the other way around, but anyway. Or like that. And the direction of the difference vector is basically the same of the direction of A or B, whichever one is larger. So whichever vector has the larger magnitude, I guess it would be B in this case. Let's make sure that B actually is larger on the right-hand side. Okay, so, whichever one is bigger wins out on the direction. Okay, so as I've mentioned these rules, but some rules for adding vectors. First of all, there's no limit to the number of vectors that you can add together to get a sum or a resultant. And addition is commutative. And if you forget what that word means, like I usually do, that just means that you can add them in any order you want. And the resultant will end up being the same. when we start doing this graphically, it might look like you would not get the same result from changing the order in which you add the vectors. And indeed, when you're doing it graphically, the shape of the figure that results from adding the vectors together on the paper may look different depending on what order you add the vectors together in, but the resultant will always be the same. And that's the important thing here. We're looking for the resultant. So if the resultant is the same magnitude and the same direction, that's what's really important, even if the vectors themselves trace out a different shape on the way to getting that result. And it's also associative. And in case you forget what that word means, like I often do, what it means is that you can, again, add things in any order you want, and that includes with parentheses. So for instance, this is true. And rules for multiplying by scalars. Remember, you can't multiply vectors by each other, but you can multiply a vector by a scalar. Multiplying by scalars is distributive, which is what I just did by grouping the scalars together and multiplying by the total. So in other words, if you have situation where a1 and little a1 and little a2 are scalars, and you have a1 times vector a plus a2 times vector a, you can group that together as a1 plus a2 times vector a. And that's what I did before, where I did, well, I was subtracting at the time, but basically it works. Subtracting is the same as adding a negative. So you can think of subtraction as a form of addition. And that's basically what I did here, where I put these two numbers together and multiplied by the result. Okay. And, oh, we're a little over the time for this segment of the lecture. So I'm going to get to unit vectors when we come back in a moment. See you then.